start a new recording here for section 3.3. Derivatives of trigonometric functions. How many remember their trig class? Okay. Nicholas remembers it. Lynn, it's one of your favorites. Well, great. Well, you know, trig functions are functions, and functions have slopes, right? If you have, well, unless it's like an asymptote. At an asymptote, you know, sines and cosines, you know, secants, cotangents, tangents. At points on those functions, there are slopes. Hence, you have derivatives of those functions. Let me give you a moment to copy this example. Okay, so we want the derivative of the tangent of x. Now, all we know right now, I mean, we have to use the rules that we learned in sections 3.1 and 3.2 to help us with section 3.3. Now, how is the tangent of x defined? Okay, sine over cosine. That's right, Ian. So finding the derivative of the tangent would be equivalent to finding the derivative of sine over cosine. Okay, and let me actually go to the next page here. So the tangent of x is sine over the cosine. So what rule are we going to have to use to find the derivative of the tangent of x? What rule is going to be necessary here? That's right, Kelvin, the quotient rule. That's right, Zoe. But of course, in order to use the quotient rule, I need to know, I mean, like, so quotient rule, the sine of x would be the f, and the cosine of x would be the g, function g. But in order to know the quotient rule, you know, since the quotient rule, again, the quotient rule in brief notation is defined as f prime times g minus f times g prime all over g squared, right? So we need formulas for the derivative of the sine and the cosine function. Well, it turns out that the derivative of the sine function is the cosine function. And the derivative of the cosine function is minus the sine. Okay, but we should ask ourselves, why is that true? I mean, right now, you're being told these two rules, but I think it's important that you appreciate why the derivative of the sine function is the cosine, and y, the derivative of the cosine function, is minus the sine. And to help you intuitively feel comfortable with that, we're going to actually rely on a concept you learned back in section 2.7, where you had functions, and then how many recall where you would have a function and then it would say match the function with its derivative, and that would have some pictures of potential derivative functions. How many recall that, where you would have a function f and it would be like a matching problem? Yes, yes. It's the same kind of thing here. What we're going to do is I've graphed. So first I'm going to show that the derivative of the sine function is the cosine function. And what I've done is I've graphed here the sine function just from 0 to 2 pi. Okay, just one cycle of it will be enough. So this is the sine wave. The sine function has an amplitude of 1. So its highest point is 1, lowest point is -1. And what I have below the sine function is a blank graph. Now let me give you a moment to copy the two graphs down. Okay. All right. Maybe another moment. Okay. So, all right, what I'm going to do is I'm going to draw some tangent lines to this function y equals the sine of x. So at pi over 2, let's start there. At pi over 2, I drew a tangent line. Okay, what's the slope of that tangent line? When x equals pi over 2, that slope is 0. Good, everybody. So that means then, so what I'm doing here, I'll even be more Thank you, everybody. Perfect, perfect. So what I'm doing is, in simple terms, okay, let me just, so this is the graph of the sine of x. Okay, let me just kind of, I mean, yes, y equals the sine of x, but this is the graph. Let's think of it as, this is the graph of the sine of x, and sine of x equals f of x. What I want to do below, is have a graph of, hold on here, one moment. I want to have a graph below of f prime of x. So the fact that at pi, x equals pi over 2, the fact that the slope is 0 for our sine of x function means that the derivative at x equals pi over 2, you know, f prime of pi over 2, would have to be 0. Similarly here, we have another flat slope here at 3 pi over 2. So also then, when x is 3 pi over 2, when our function equals 3, when x equals 3 pi over 2, the derivative of our function equals 0. So I put the, you know, so I'm plotting points for my derivative function, and I want to plot enough points so that I can, you know, connect the points and draw the derivative function, f prime of x. That's what I'm doing. Okay, but we need a few more points, right? It's like Wheel of Fortune, you know. We don't have enough information to solve the puzzle, right? And so, okay, well, what about at 0? Let me draw a tangent line at 0 there. What does the slope look to be there at when x is 0? What's the slope of the tangent line? Right there at x equals 0. It's positive, and could you sort of guess a value? If you had to guess, if you had to make a good guess. 1, that's right. That's right, Nicholas. So, okay, so when x equals 0, the slope is 1. Make a little. Okay, are there any questions so far? All right, let's proceed on here. What about at pi? That's an interesting value. Ah, that's right, Lynn, -1. That slope's going to be -1. So the derivative function would equal -1 when x is equal to pi. Good. Okay, let's pick one more interesting value here. At 2 pi. Slope is 1 there. That's right. Very good. Nicholas, Anna, and John, everybody's getting the feel. So then there's 1. At x equals 2 over pi, and when at x equals 2 pi, f prime of x has to equal 1. Well, do we have enough information to graph our derivative function? Sort of. I mean, technically, we maybe should take some more values, but if we were to connect it, I think you'd agree that the derivative function, hold on here, let's try to make it look good. We spent some time doing this, right? See, I can use the white to kind of erase. That's pretty cool. Tell you what, would any of you like to try to draw the, I'll tell you what, I'll let you do it on the next one. Okay, let me do this one. Oh, wow, what does that look like? What does that function resemble? Or what is that function? The cosine, there you go. There you go. So f prime of x equals the cosine of x. So when our function is equal to the sine of x, the derivative of that function is the cosine. And you've basically done a graphical argument to show that result. How many think that's absolutely cool? Yeah, absolutely. We can do the same thing now for the derivative of the cosine. The derivative of the cosine is negative sine, that's apparently. So let's go to the next page. Are we good? Are there any questions? All right. So now we have y equals the cosine of x. Okay, and I'll express that as f of x equals the cosine of x. Okay, and what we're going to do is just like before, we're going to take some slope, we're going to draw some tangent lines to key points on the graph. Right, Nicholas? Well, Ian, let me see. Ian's asking if the second derivative equals negative sine. The second derivative of the sine. I'd have to think about it. I should know, but I just don't think so quickly. I'm just, so, yeah, I mean, once you get a derivative, then you can take a derivative of that derivative to get a second derivative. But I don't want to call out an answer because I'd have to think about it, and I'm not, right now I want to get these points plotted for my f prime of x. Ian, you might have a chance to explore that over the weekend in homework. Okay, let me see here. I don't think I want my, yeah, that's fine. That's fine. Okay, so let's get a few more tangents here. let's see, Nicholas says that derivative of sine is a cosine, derivative of cosine is minus sine, and therefore the second derivative of sine is hold on. All right, one moment. Yeah, I just can't think about it, guys, right now. I can't, during classwork time, I'll look at that, okay? I'm afraid to answer too quickly. I've gotten, you know, let me see here. So let's, okay, and then we have some, what's the slope of that tangent line? I know it's not perfect, but what's the slope there? -1, okay. And then you have the slope of this tangent line. That's going to be +1. So you're all getting, I think, the idea here. You're getting the idea. You're getting the idea. And so f prime of x does equal negative sine of x. If you take the sine of x and flip it, okay, you had in trigonometry, you learned how to take trig functions and then negate them. It's like taking a -1 as a sine. So every, like the sine function, of course, I mean, you know how the sine function looks. That's the sine function in the dashed purple. And if you, then the negative sine of x would be just the reflection about the x-axis. And so now we've established that the derivative of the cosine of x is minus the sine of x. And now we're ready to solve this problem. Are there any questions so far? All right. May I move to the next page, or I want to make sure I'm pacing myself well. Okay. Well, so now, again, the derivative of the sine over the cosine, we're using the quotient rule. So the quotient rule says then you take the derivative of the sine. That's, well, hold on here. Let me just, it's still kind of new for you. So all, you know, you have f and you have g. So then the derivative of the quotient is f prime times g minus, hold on here, one moment. Minus f times g prime. So the f times g prime, I have it a little bit, I mean, it's still mathematically correct, okay? I normally put, for this part here, I would have normally put sine of x times the cosine of x prime. I would have reversed the order, but I just had it that way. And that's okay. That's okay. And then it's over f over g squared. Okay. Okay, and then you just do a little bit of math. But are there any questions on this step here? All right. Well, so the derivative of the sine is the cosine. Derivative of the cosines minus the sine. And you're left with cosine squared plus sine squared over cosine squared. We know the cosine, by the way, we know that the cosine of x, quantity squared, can be written as, in this notation, cosine squared of x. Okay, how many recall that from their trig days? Sure. Oh man, Rodrigo. All right. Well, you're learning something new here. Hey, what's cosine squared plus sine squared equal to? Isn't that equal to something special? That equals 1. That's right, John. That's a Pythagorean identity. And so you get secant squared. So the derivative of the tangent of x, one moment, I'll get that question, Ian, hold on. The derivative of the tangent of x equals secant squared of x. Let me see. No, cosine squared plus sine squared is, oh, I see what you're saying. Can secant squared be written as 1 plus, what Ian's saying is, can secant squared be expressed as 1 plus tangent squared? One moment, let me check on that. One moment. It can be, that's right. Secant squared is equal to tangent squared plus 1. But secant squared looks a little, you know, it's a little briefer answer. All right. Now there's, hold on here, one moment. Let me, just got out of my, I mean, I'm not like looking at my email, but I had it open, and I don't want, you know, the beeping to go on here. So okay, now in the book, by the way, there is a table of rules for trigonometric functions. What I mean is a table. It's at like in section 3.3 towards the last part of the section. Well, or towards the end of the section, just before example 2, they have derivatives of trig functions. So you've learned what the derivative of the sine and the cosine and the tangent are, but you could also similarly derive the derivative for the cosecant, the secant, and the cotangent. And the table has those derivatives. So there's a table you can refer to. Are there any questions? I think we have time for one more example here, and then I can let you do some classwork. But are we good so far? All right. Well, then let's try one more here. One more example. I'm thinking about you when you work on your homework. Okay, let me give you a moment to copy this one down. Okay, so we have this function of theta equal to the secant of theta over 4 plus the secant of theta. And we want to find f prime of theta. We want to find its derivative. So again, we're going to have to use the quotient rule here. Okay, but it's going to require us, of course, to figure out what the derivative of the secant is. All right, so let's go ahead and start the problem off. Okay, so again, I have my f function, and I have my g function. I got to be a little careful here. I'm using well, let me not do the f over g thing, because we got this, we have our function little f defined here. I think you know how the quotient rule works. We're going to take the derivative of the numerator and multiply it by the denominator, and then subtract the numerator times the derivative of the denominator, all divided by the denominator squared. I like it in this form because I just like things, I just like it in that form, you know. And of course, for your next exam, you know, a problem like this, I would want to see this step, you know, I would want to see your work. I don't want to just see an answer for a complicated derivative like this. I want to see you justify your answer. But of course, now, the issue is here, how do we find the derivative of the secant? That's the question. If we can get that, then we're going to be okay. So the derivative of the secant would be the same as the derivative of 1 over the cosine. The secant function is defined as 1 over the cosine. How many remember that from their trig days? I hope it's more than that. Oh my, Rodrigo, oh my goodness. We're going to, all right. Well, Rodrigo, you're learning some things here then. The secant function is defined as 1 over the cosine. Okay, so if I want to take the derivative of 1 over the cosine, I'm going to have to use the quotient rule. I'm going to use the quotient rule here. What's the derivative of a constant? What's the derivative of, these are primes, right? These are primes. They stand for derivatives, right? 0, good, good. So, all right. And the derivative of cosine, we've established that to be minus sine. Good, everybody. And so I'm going to get sine over cosine squared theta. But we can write that in a little bit nicer way. We can write this sine of theta over cosine squared theta. We can write that as 1 over cosine theta times sine theta over cosine theta. And that would equal the secant of theta times the tangent of theta. It's nice to write it that way because then you don't have a fraction. All right, are there any questions? We just proved another rule, derivative rule. The derivative of the secant function is secant theta tangent theta. And incidentally, you notice now, because my independent variable is theta, I'm differentiating with respect to theta. I mean, would it make sense to say, would it make sense to do this? The derivative of the secant of theta with respect to x, would that make sense? It wouldn't make sense, although technically that would equal 0 because secant of theta is not dependent on x. It's like a constant with respect to x. But we would not, but you know that, you know, we would, if we're differentiating with respect to theta, we have to have the we have to have d theta, right? Or it just doesn't make sense. And that's something also I'll look for in your work, right? So, okay, let's go to the next page if we're good. Okay. So now we're back to f prime of theta. Hold on, Trevor, wait. Let me go back, one moment. Okay. So we've established that the derivative, okay, you're welcome, Trevor. The derivative of the secant of theta, you're welcome, will equal secant of theta times the tangent of theta, right? And so now we'll go back to our, where we left off. Now for f prime of theta, we're going to substitute in the derivative for secant prime of theta. And we have to substitute in the derivative for 4 plus secant prime of theta. Well, the derivative of 4 is 0. So both of those expressions, both of those derivatives, you're going to put in secant theta tangent theta. And you'll notice then that secant theta, tangent theta is going to be a common factor. I mean, I certainly don't want to type all this in WebAssign. So, you know, I'm going to simplify the answer. Secant of theta, tangent theta factors out from the numerator, leaving me with 4 plus secant theta minus secant theta as the other factor. And then, oh, isn't that nice? The secant thetas drop out. And so this is your answer. For f prime of theta. F prime of theta equals 4 times the secant of theta, tangent theta, all divided by quantity 4 plus secant theta squared. It's just amazing, you know, you prove a few rules and you can do wonderful things. I mean, now you're able to find derivatives of harder functions than you had found before, more difficult functions. And one thing, that's right. I think Nicholas is liking this. Who thinks this is kind of cool? Thank you, Betsua. Yes. Thank you, Anna. Thank you, John. All right, lots of good things. Thank you, Rodrigo. And one thing I want to point out, something I noticed, because you see, when I like assign the homework, I can also see like the answers to the problems, and I noticed like for this this answer, 4 secant theta tangent theta divided by quantity 4 plus secant theta, like in WebAssign, they put parentheses. They put parentheses around the thetas. So you'll notice, like in my answer, I just have, like, for instance, I just have secant of theta without a parenthesis around a theta. But when I see answers, it seems they're always putting thetas. They're always putting parentheses around the angles. So you want to get used to that because, you know, as you know, on like exams for free response questions, you have two tries, right? Because one's if you have a typo, and another's if you, I mean, you know, really it's 2 tries because you could have made a typo. But, you know, try not to make a typo, right? So I would recommend when you write your answers to have parentheses around the angles in your trig functions. I mean, you could try doing it without the parentheses, but WebAssign might complain. So I would recommend getting used to putting parentheses around your angles. I think I would recommend that. I do recommend that because I think I have seen in the past a student get an answer wrong because they didn't put parentheses around their angle. So, all right. Are there any questions on that? Any questions? All right. Very good. Very good. And I'll mention in section 3.3, they talk about analyzing the motion of a spring. I'll just bring this up, and then I'm going to. Our class ends at what? 6:15. So another 10 minutes. We ought to be able to let you do some classwork, and that'll. But I want to just bring up this example real quick in section 3.3. May I stop the? Is everybody good with the example? We're good. Everybody has it copied down? Okay. Okay. So let me see here. Let me get the ebook here. Okay, so chapter 3, differentiation rules. And we're doing derivatives of trig functions. And I want to get to the third example here. Okay, there's that table, by the way. Derivatives of trig functions. There's that table that I mentioned. So they talk about an application analyzing the motion of a spring. And this is something that's going to be important for like engineering and physics classes. They talk about an object at the end of a vertical spring that's stretched 4 centimeters beyond its rest position and released at time t. Okay, its position at time t is equal to s equals 4 cosine of t. So they're assuming that you know, this spring is in like a vacuum. In other words, there's no air resistance. You know, you stretch the spring and release it. It's going to bounce, boing boing boing. It's going to go up and down, up and down, up and down. You know, forever. How many have noticed that a spring, if you release it, it will, like a slinky, or you know, it'll bounce up and down? How many have kind of seen that? A spring in action. Okay, Lynn has not. Well, if you release the spring, but this spring is assuming this is like this is sort of just a very simple example. Very simple example. Okay, this spring, what's going to happen is the mass is going to move up and down, up and down. So right now, see, if in figure 5, the spring is stretched and the mass is at position 4. That would be s equals 4. When time equals 0, the cosine of 0 is 1. So 4 times 1 is 4. But when you release the spring, when you just, you know, you're holding the mass, and if you release the mass, the spring stretch. Well, what's going to happen when you release the mass? What's the spring going to do? If it's stretched and you release the mass, what's the spring going to do? Is it going to expand more, or is it going to contract? Is it going to expand or shrink? It's going to contract. So that's going to cause then, is the mass going to move up or down? If the spring gets contracted, the mass is going to move up. That's right. Well, the mass will have to move up. Now, what's interesting is the way the axis is, the vertical axis in this problem, is that like you're used to a vertical axis, negative values being below 0, positive values being above 0. But here, the negative values are actually above 0 going up. Okay, and it's just because how the problem's oriented. So they want you to find the velocity and acceleration and use them to analyze the motion of the object. Well, what's velocity relative to position? How do you find velocity based off of position s? What do you have to do to the position function? That's right, you have to take its derivative. And if you want to get acceleration, how do you find acceleration? Acceleration is the derivative of velocity, or, very good everybody, the second derivative of position. And so what they're doing here is since you know now how to do derivatives of trig functions, they find the derivative of the velocity. They find the velocity, which is the derivative of position, and then to get the acceleration, they take the derivative of velocity. And they talk about how if you look at the graphs of these functions, how the object will oscillate between s equals 4 centimeters, which will be the low point, to the highest point, s equals -4 centimeters. We do the exact same kind of thing in differential equations, Math 282 problems like these. So, you know, they go through some detail in the problem where they actually graph the position function s, the velocity function v, and the acceleration function a. Okay, and you notice, like, for instance, this is figure 6. Well, position 0 is actually the equilibrium, what we call the equilibrium of the spring. When the spring is neither stretched or compressed, the mass would be at that 0 value. And you know, I think once you work it, you'll see the drawing maybe will make better sense in time. But you notice here with the position function, like when s equals -4, okay, like in figure 6, when s equals -4, that's when t equals pi, right? When t equals pi, the position of the mass is -4 after pi seconds has elapsed. Well, what's the velocity at t equals pi? When time equals pi, the velocity, the position of the mass is -4, and the velocity is 0. But does that make sense? Does that make sense? Because when the position of the mass at t equals pi, when it equals -4, is the spring, I mean, is the spring like completely stretched, or is it completely shrunk at that t equals at t equals pi, when s equals -4? Would the spring have to be compressed, like the most it can be, or stretched the most it could be? Well, it actually would be compressed, because that's right, Betsua. And I appreciate all answers, Nicholas, everybody. I appreciate all answers. Remember, look at the graph here. You know, when s equals 4, the mass is the spring is stretched, but when you release it, the mass goes up and it'll go up to -4, and that would be the spring would have to be compressed. So this problem is you know, an interesting problem, and you'll see it. You'll work with a few problems dealing with that kind of scenario. But on that note, what I'd like to do is stop the recording.